שלום לכולם, אני שמח מאוד לראות אתכם כאן. ברוכים הבאים להרצאה הראשונה בסדרת ההרצאות שלנו של טבולה, של קבוצת האלגוריתמים, שהאמת שקראנו לה אלגו ווינטר טוקס, יצא קצת שמש בחוץ, עוד לא נכנסנו לחורף באמת, אבל נסלח על זה. את ההרצאה הראשונה יעביר אביב רוטמן, ראש צוות בקבוצת האלגוריתמים, 5 שנים בטבולה, ידבר קצת על הארכיטקטורה שלנו, ואני מזכיר שזאת ההרצאה הראשונה מבין סדרה של 7 הרצאות, 2 הרצאות בחודש, שכמובן אנחנו נקפיד לעדכן על ההרצאות הבאות.
סליחה, אפשר לעשות את זה באנגלית אולי? כי אני רואה שיש אנשים שלא מדברים עברית פה.
Rotman, it's up to you. Are you good for English or?
Yeah, let's go.
Because most of the people are Hebrew speakers, but I see that there are a few who speak English. Indeed.
Let's do it by a raise of hands. Stop. Okay, let's see if I can do it. It's actually a good idea. I've done this talk in Hebrew already, and it's on YouTube, so let's do it in English. Okay. So hi everyone. My name is Aviv. As Aurel said, I'm a team leader in the algorithms department in Tabula, and just some technicalities. It'd be great if everyone muted themselves, and if you have questions, please write them in the chat, and I'll stop a couple times during the talk, and we'll read the questions and I'll answer them. If there's a question that you can't wait and you won't understand anything during the rest of the talk, then feel free to break out of mute and say something. Another thing regarding questions is you might want to keep them till the end, because we're going to do some breakout rooms, and there'll be an algorithm engineer or 2 from Taboola in the breakout rooms with you, and you'll be able to ask questions and develop a discussion with them in a more intimate setting. So let's get going. So I'm going to talk a bit about some lessons that we learned while building our recommender system using deep neural networks in the past couple of years at Taboola. So who is Taboola? Well, you've probably seen us before. Can everyone see okay? Is the screen okay?
Yep.
Okay, cool. So who is Taboola? You've probably seen us before. We're the content recommendations at the bottom of articles you see on sites on the internet, like Ynet or Calcalist or The Independent or Business Insider. And we have 2 flavors of recommendations. We have organic recommendations, which means it's, let's say, The Independent, and we help them recommend other items in The Independent so that you stay on The Independent longer. And the other flavor is sponsored content, which means that other sites on the internet pay us to show them on The Independent. And then when someone clicks, they pay us, and we split that payment with the publisher, which is again The Independent or Bloomberg. And so I'll call these sites publishers, and I'll call the people who pay us, the sites that pay us, I'll call advertisers. So how is the talk going to be built? I'll talk a bit about the problem setup of recommending things on the internet. I'll speak about the challenges of that setup. I'll discuss quite in depth the architecture that we chose in order to solve this. And I'll speak about a few kinds of features that we've integrated into this architecture. So this is the Taboola widget, and our job as an algorithm team is to decide which 3 or 6 or 9 target to recommend to the user in order to maximize both Taboola's and the publisher's revenue. And how do we do that? So we try to calculate the estimated revenue that we can make by taking the CPC, the cost per click, the cost that the advertiser is willing to pay for a click, on a specific item, and the probability of a user to click an item. We call that probability the CTR, the click-through rate. We then multiply these two numbers, the CTR and the CPC, and rank all the items on the result and choose the top 3, top 6, or top 9. Now, we can address CPC as if it's a given, and what our model actually does is try to estimate the CTR. So how do we estimate the CTR? We have a couple ways, quite a lot of information to do that. We have contextual data, which is, let's say, data of where the user is browsing from, where in the world, what platform, what browser. We have a lot of historical features regarding the user. We've seen them multiple times on the internet. We know what Taboola items they click on. We know what they read. We have contextual data where the user is right now, what publisher he's on, they're on, what they're reading, and we have a lot of information regarding the content that we want to recommend. We have pictures, thumbnails that are related to the ads. We have the titles. We know who the advertisers are. So we take all that, we stuff it in an algorithm that we'll talk about a bit in a minute, and we outcomes the CTR, the probability for a click. Why is that hard? Well, one thing is that there's no real human baseline for recommenders. If I wanted to decide if a picture was a dog or a cat, I could go up to any one of you and show them a picture and ask them if that's a dog and a cat, and most certainly I'd get a true label. If I walked up to one of you and said, here's 1,000 items, can you tell me which item I should recommend for this user right now? Probably wouldn't know what to answer. And also, if I asked 2 people, they'd have vastly different answers. So there's no real baseline. Also, we have no explicit feedback. What does that mean? If a user clicked an item, it might mean that they're interested in that item. But if a user didn't click an item, it could be that they looked at somewhere else in the page. Maybe they heard something in the background and they weren't paying attention. Maybe they clicked another item in another widget that's not Taboola, and it doesn't really mean that they're not interested in that item. And that can add a lot of noise to our signal. And last, the data that we have is very sparse and constantly changing. We have millions of new users every day, and thousands of new recommendations that we can choose from. So we have to deal with that, with a constantly changing world. This is, so I'll just, we'll do a history lesson a bit and build up to how, to the model that we're using currently. So let's go back in time to 2006. Netflix, I'm sure you've heard of them, released a challenge they called the Netflix Prize, in which they gave a list of users and their ratings for movies and a list of movies. And they asked the world, please recommend to users new movies that they've never seen in the best way possible. So in fact, what they gave us was a matrix where each row is a user and each column is a movie, and wherever a user rated a movie will have a score from 0 to 5, 1 to 5. So in 2006, a relatively unknown developer blasted everyone away. They weren't a machine learning expert or a recommender systems developer. And what they proposed was this. We'll factorize that matrix into 2 new matrices, one that represents the users and one that represents the movies. When doing a dot product between a vector from the user matrix and a vector from the movie matrix, the result of that dot product will be the estimated rating. And that won the Matrix prize for that year, the Netflix prize for that year, and they called that algorithm matrix factorization. We can easily port that over to Taboola. We just need to change movies with ads. We call those ads interchangeably items or targets. And we'll just change ratings with clicks. So if a user saw an item, then and they didn't click it, there'll be a 0. And if they did click it, there'll be 1. And when we do the dot product, we'll get the CTR, the probability for a click. Now, what's the problem with matrix factorization? Matrix factorization doesn't handle unpreviously seen before users and items. We call that problem cold start. And there's absolutely no way to deal with it with matrix factorization. And it also doesn't use a lot of data we have available regarding the items and the users, if it's textual data or the thumbnail or things we know about the user, categorical things we know about the user's context, and so on. So what kind of algorithm do we have that knows, on the one hand, to generalize and deal with cold start, and on the other hand, knows how to deal with complex features like text and images. So what kind of family of algorithms? I'll answer that. It's a rhetorical question. Deep neural networks, right? And that's what we're here for. So how do we rephrase the matrix factorization algorithm as a deep neural network, or at least a neural network, not very deep? So what we'll do is we'll learn those vectors, those vectorial representations, and we'll call them embeddings. The word embedding is taken from the word-to-vec algorithm, where we try to learn a representation of words by predicting the words that are around them in a sentence. So here we'll learn the representation of the target, of the item, and the user. And what we'll do is we'll just create a random vector for every target and for every user. Then we'll go over our examples. We'll do a matrix. We'll do a dot product between these vector representations that are currently random, and we'll try to predict if there'll be a click or won't be a click. And slowly, through gradient descent, we'll fix these random vectors. We'll fix these weights, and they'll come to represent the user and the target in such a way that when we do a dot product, the estimation will be precise, just as precise, or at least as precise as in the matrix factorization problem. And it's kind of easy to understand how now I can add other features. All I need to do is create for an embedding for those other features, like the article the user is on now, or the publisher that the user is reading at, and create a random embedding for them. All I need to do is a dot product everything and everything, use the results of those dot products to try to predict if there will be a click. And again, gradient descent will make those embeddings be precise and represent whatever category I'm talking about, if it's the article, the publisher, the target, the user, in the context of trying to predict a click or of trying to predict a click. Now, that also shows us how we can deal with the cold start problem, because let's say I had 0 instead of a user ID, I still would have the embedding of the article the user is at, publisher, and I could use that to do a dot product with the target ID and get to some form of result that might not be as precise, but still tries to predict a click. Now, what's the problem with the previous algorithm, which is called factorization machines, by the way? In a complex world, it'll be hard for my algorithm to understand the following thing. If I try to do an interaction between the target, let's say, and the publisher, and the user, and the same embedding of the target, things might get mixed up because it's not the exact same interaction. So it's sort of like trying to open a round lock and a square lock using the same key. So what can I do? I can easily learn an embedding for every interaction. So let's say I do an interaction between the target and the publisher. I'll learn one embedding for the target, and I'll learn another embedding for the target when I do an interaction between the target and the user. And I can also group targets, group features into families. where I know something about each family. I know that they share this a bunch of features like characteristics, and I know that when I interact families with each other, they'll behave similarly, and I'll call these families fields. And I'll learn an embedding when for each family when they do an interaction with another family. And this algorithm is called a field-aware factorization machine, which is a family of fields. And that's what we use in production today. But let's say I want to describe interactions of a higher degree, let's say three-way interactions or five-way interactions. Well, I'm a person who's learned deep learning, so I'll do what every good deep learning practitioner does, and I'll just pour some dense networks on my model. And that's indeed what we do, and this is how our model looks in production. But the main takeaway message I want you to understand is that this FFM, field-aware factorization machine, allows you to do the following. Take any feature, create an embedding of that feature of a certain size, which you decide for all the features together. Do a dot product between all those embedding, and try to predict the click. That's it. Any feature, I can add any feature by just bring, it can be categorical, it can be complex, like a picture, it can be just a number, bring it to the right embedding size, and plug it into the network. And we'll, in a second, speak about a couple kinds of features that we put into our network, but now might be a good time to take some questions. So if there are any unanswered questions, because I've seen you guys been chatting with each other in the chat, if there are any unanswered questions, or if someone wants to break out of mute and ask a question, now's the time. I see that the other algo guys and girls have been prolific, so all the questions have been answered, or everyone's waiting for the breakout rooms. So let's speak about a couple of the features that we put in our network. And we'll start from the user history. So this is a user, and they come quite frequently to Taboola publishers where Taboola is installed. And we show them targets, and they click on some of these targets, and on some of these targets they don't. And these targets have categories like sports and news, and they have advertisers. And we save this history and can use it as a feature. How can we use that as a feature? So I gave you the answer only 2 slides ago. I want to embed the history. But how do I embed the history? So we do a bag of words. So in this case, it'll be a bag of categories. And what does a bag of categories mean? We just average everything. So we'll take all the categories a user clicked on, and we'll do an average of all those categories, and we'll hope to get an average embedding of the categories the user prefers to click on. So that average that we did is weighted by clicks, right? If the user didn't click on news, we won't put it in the average. But not all categories are equal. This user clicked on on the tech category 9 times, and they clicked on the sports category 90 times. So it might make sense for this user to do a weighted average and emphasize the sports category, right? So we can weight the average using the clicks, right? No, wrong. I was leading you on. The only reason this user clicked so many times on the sports categories is that spamming them with sports related articles. But in fact, this user, almost 1 out of 2 times that I recommend a tech item, they'll click it. So they clearly prefer tech over sports. And maybe I should use the clicks and the views together. And I'll actually weight the different categories by their CTR, by the click-through rate of a user on a category. And that's indeed what we do in production. and that's one of our most important features, the history the user has, the click history of the user. But the sky's the limit with these kind of sequential features. We can learn an attention layer and integrate some context. So if this user is clearly likes tech, but they're in a sports publisher, let's say ESPN, then suddenly it might make more sense to emphasize sport, right? So we can use attention for that. Or if we think that the sequence of clicks makes sense or has some form of information in it, then we can use an RNN to embed the sequence. And on and on and on and on. Again, now is a good time to stop for questions. Is there anything everyone hasn't answered? Oh, and I want to take the one on the transfer learning. Please wait for our next winter talk, which will talk specifically about transfer learning, how we use that at Taboola. This message has been brought to you by Taboola Winter Talks. So let's talk about, you guys heard the word deep architectures. And up until now, I've been speaking about some cool architectures, but they haven't been particularly deep. Let's speak about some actual deep stuff. So again, this is a Taboola widget, right? And a user who sees this widget doesn't know anything about the advertiser. They don't know about their click history or the click history of users that look like them. They only see the thumbnail and the text, right? And that's how they, more or less, how they decide if they're going to click or not. So there should be enough information in the thumbnail and the title of the item to help us predict if this user will click on this item or not. We're data scientists who love deep learning, so we should be able to find some cool algorithms and architectures that can deduce something from complex features like the image and the text. And in fact, we use these complex architectures like CNNs and transformers. And there are two ways we do that. We can either learn embeddings for these complex features like the image and the text and the title as part of the FFM that we train on the click. And we can also, if we're talking about a deeper, more involved network that might take more time, where it's harder to train and needs more examples, we can take an algorithm, either download something pre-trained from another research group or pre-train it ourselves, then take the features, let's say the image, ask that a network for the embedding, save that embedding in a database, and then when we come to infer or to train our model, we can grab that embedding from the database and use it as a feature. So we did that. We learned our own word-to-vec model. And the reason we needed to learn a word-to-vec model that we learned was that we came to understand, is that, let's say in Wikipedia you learn word-to-vec and queen is closest to king. In our data, king is closest to size because most of our data is advertisers and we have advertisements for mattresses. So it was pretty crucial to move from pre-trained embeddings from other research groups to pre-trained embeddings that we learned. And here's a nearest neighbor search from our tensor board on an embedding, a word-to-vec that we learned on organic titles. And what I did is my query was Celtics, the NBA team that plays in Boston. And indeed, you can see here in the lower right corner that I found other NBA teams like the Clippers and the Pistons and the Raptors, which I'm partial to because I'm from Toronto. But a bit less nearest neighbors were a cluster of other teams that are NHL and baseball teams. And a bit further away are also NFL teams. And I think it's really non-trivial that our model managed to learn both the fact that these are all sports teams, but also managed to cluster different sports in different areas of the feature space. That very same model not only learned the semantics of our corpus, but it also learned grammar. You can see here the word, I did a nearest neighbor search on the word amazing, and I found other adjectives like incredible and awesome. And when looking for amazingly, which is pretty similar to amazing, you'll have to agree, because you can't speak. Amazingly is very close to other adverbs, rather, like absurdly and surprisingly and astonishing. So I think that's pretty cool. And when doing entire sentences that should combine the semantics and the grammar, we can see some really, really non-trivial results. Like I queried how diverse technologies will end our water crisis. And I found a lot of other items of like the following formula: how technology X will help something that helps humanity Y. So you can see other titles like how banking cord blood is unlocking new medical treatments, and how data is helping meet new healthcare goals, or how self-service technology is enhancing the guest experience. I think that's really cool. One second. Okay. So another cool example, again on organic data, is I put in a sentence regarding the fact that Stephen Curry won't be playing in the next game against the Spurs, and I found a bunch of other items related to both Stephen Curry, but also other players not playing in the next game or the next season because of being injured or because of signing up for another team, but of a very similar meaning. So that's it for titles, but we also have thumbnails, and images present a different problem. We don't have enough images in our corpus to learn a full image model, which requires quite a lot of data. But our images aren't that different from, like the world. It's just images, right? So we took a pre-trained model that was trained on the ImageNet dataset, and we then extracted embeddings from that model, and we did a nearest neighbor search again. And let's say I input cars, so here I can see cars on the right, which is pretty trivial because there's a lot of cars probably in the ImageNet dataset. But when I put people looking at screens, which is probably something that doesn't exist in ImageNet, I found people looking at screens, which is something that's probably unique to our dataset. And when combining text and image, I can find some really, really, really minute differences between items. Let's say I'm looking at cheap flights to the UAE, which this actually example wasn't chosen in the recent past. It was a couple of years ago we found this example, and it's still relevant today. You can still try to look for, or even more relevant now that you can find flights from the UAE from Israel to the UAE. So on the right, you see items related to civil flights. I was looking for the word, and on the left you can see civil flights, and on the right you can see fighter military aircrafts. When I looked for an article called "Top 10 Fighter Planes," and I'm not even sure that I'd be able to tell the difference between civil aircrafts and military aircrafts from these pictures, but our model was able to do it by combining it with the text. And we took all this really rich data of the text and the title and the image, and we just plugged it into our network as a feature. And that brings us back to the message I tried to say earlier, that this FFM, what we find really good about it is that you can combine any kind of feature, and you saw that we can combine some really complex features like ImageNet, like images with ImageNet, and this generative LSTM that we saw that embeds the titles, and it can be just a category like publisher ID, and it can be a a sequential feature like click history. And you just need to think about how to bring that feature to be an embedding of a certain size, and that's it. Another cool thing about that, other than the fact that we have, as a recommender system for articles online, we have various kinds of, like, lots and lots of features of different kinds that we constantly think of and need to integrate into the same model, is that, as Orel mentioned, we're quite a large group of algorithm engineers, and a lot of us work on the same model. So with this architecture, we don't need to redesign the entire network every time we add a new feature. We do talk to each other regarding experiments, but technologically, we just need to add the feature to embedding, put it in the network, and no one else knows the difference. I'll summarize by saying recommendation systems are dynamic and challenging to model. And although one may think that deep learning models are sort of a one-size-fits-all architecture, you need to really put some thought into the architecture that you're using, depending on your problem and your setup and how people are working on it. And again, modeling does matter. It's not enough to just add an embedding and add a million dense layers. You need to really think of your features and how they should fit into your model. And that's it. Thank you. And now I'll explain a bit about how we're going to do these breakout rooms. What we'll do is, in a minute or two, we'll split into a couple of rooms, and there'll be an algorithm engineer too from our team that will be able to take questions. And if you don't have any questions, we'd love to hear how you guys deal with similar problems, like how you combine features from of different kinds in your algorithms, and if it's with deep networks or without. And we just love for you to share. So with that.
כולם חזרו אלינו?
זה עם וידאו בטוח, לא סתם.
כן, וואו,
מעולה. מעולה. אז אני מקווה מאוד שנהנתם בברייקאוט רומס, שהייתה לכם הזדמנות לשאול באמת שאלות את החבר'ה מהקבוצה אצלנו, מקבוצת האלגוריתמים. מקווה שלא קטעתי אתכם באמצע השאלה, זה היה אמור לתת נוטיפיקציה של 60 שניות. מקווה שנהנתם מההרצאה, שזה היה עבורכם מועיל. כמובן שיש את העמוד הרשמה להרצאות הבאות, אני שלחתי קישור לעמוד הזה בצ'אט, אני מזמין את כולכם להירשם גם להרצאות הבאות. יש שם גם פרטים ליצירת קשר, אם למישהו עדיין יש שאלות שהוא רוצה לשאול והרגיש לו בנוח לשאול בפורום הזה, או אם יש עוד רעיונות, תרצו לשתף משהו או באמת שוב לשאול שאלות, אני מזמין אתכם לשאול גם שם, ונתראה בהרצאות הבאות.
תודה רבה.
תודה.
רגע, מישהו שאל על ההקלטה, הולכת להיות הקלטה מפורסמת, לדעתי מי שפה יקבל על זה מייל, ואם לא, אתם מוזמנים לעמוד היוטיוב שלנו, טבולה אנג'ינירינג, שם יש אפילו, יש הקלטה של זה בעברית, של ההרצאה שהייתה היום. אז ביי לכולם.